So please, Daniel.
So thank you very much for having me here. So thank you, the organizers, Dario, who's not here. And what I'm going to tell you is about some methods we've been developing for the last few years concerning what we will call dimensionality reduction. But actually, I'm going to focus on quantum dynamics. So our interest basically is to solve the Schrödinger equation. We are in the community of the MCTDH method, multi-configurational time-dependent Hartree method, which is a very efficient software method to solve the Schrödinger equation, time-dependent. So to propagate high-dimensional wave packets. And in this sense, there's a big need to have compact and accurate representation of operators. In particular, we're going to focus on the potential energy surface, but any operator which is going to be expressed on it, as I will describe later, can be applied. This method can be applied to it. So as you see the title, I'm going to talk about low rank. This is the important thing, low rank. Low rank, so this means small size, analytical representation. So basically what we're doing is just taking a tensor decomposition method and turning it into an analytical expression. And this analytical expression will have a very nice interpolation properties, as you will see later. See? No. No, it doesn't. Wait a second, it doesn't seem to like this. Again. Sorry. Nope, not. I think I'll change the pointer because it's not working.
Juste appuyer.
Oui, je le fais. Je le fais.
Non, appuyer sur le.
Très bien. Ah ouais. Sorry about that. Oops. Yes, no, it's fine. Okay, so here's the outline. I'm not going to stop. So I'm going to describe these grid-based representations which are needed in our approach to quantum dynamics. Then I will talk the classical Tucker decomposition, and I will tell you why and how to transform this into analytical expression, which we call sum of products finite basis representation. And then we tackle the problem of canonic polyadic, which is a different family of tensor decomposition methods. And then I will finish with some future perspectives and conclusions. So the problem we are facing is the following. We've got a molecular system for simplicity 3D that we can see on the screen. So we've got water molecule, we've got 3 degrees of freedom. And then in quantum dynamics, the way we do that, we digitize the configuration space. So essentially, you take a number of points, you assume a number of discrete structures for this degree of freedom for that one and that one, and you end up with a dimensional, 3-dimensional grid. And of course, if your system has 3n-6 degrees of freedom, then you've got n larger than 3, you end up having something which is high dimensional. And of course, you've got this exponential increase in the number of data points, and obviously the concomitant number of operations you do with those data points. So something to take into account is the fact that this primitive, what we call the primitive grid, is given by the problem you're studying. If the energy content of your system is larger, you will need a larger density. If you're dissociating something, probably you need a larger grid. So the grid side is dictated by your problem. So we start from some coordinates, and then we map them into a grid. I put this small symbol just to refer to what we call the primitive grid, which is the one you need to do quantum dynamics, the one that guarantees that your wave function is going to be converged. Then any property you're going to use, any property, say the Hamiltonian has your kinetic energy term, then you can have any field, you can have your potential energy surface, of course. All these properties will be mapped, also, of course, on this grid, so that the potential, which depends on the coordinates, now will have a representation in which the potential depends implicitly on some indices, which corresponds to a grid point, and a grid point being, of course, a configuration of the system. And then the potential index space will look like this. We are going to use sometimes these composite indices. Okay. So now in this representation, you've got a tensor, which is in the computer science, it's called, community is called multidimensional array, which is some sort of a bunch of a bunch of real numbers, and these big N1, big N2, and so on and so forth. These are just the number of points you decided to discretize your specific degree of freedom 1, 2, or n. And of course, this leads to exponential scaling and the well-known course of dimensionality. Just to give you a couple of examples that on which we are working or we worked already on. So we've got this B hydroxide molecule, which is a 5-atom system, 9 degrees of freedom. And then you need typically of the order 10 to the power of 10 grid points. If you do LS minus LH, you end up having this size of potential, typically over the hundreds of gigabytes. If you do 2 electron dynamics coupled with a continuum, then this number is, even though it's a 60, typically, actually, just to be fair, we work in, for some reasons, we work in Cartesian coordinates. And to be fair, you've got these 10 to the power of 12 grid points, and this amounts up to this. So this starts to be something which is not doable in a node, cluster node. Okay, so it's not practical. And for the system I'm going to present you, we will need of the order of million gigabytes. So we have to do something, and obviously the solution for that is to be able to reduce this somehow. So just to give you some more features of the problem we're dealing with is the fact that this tensor, these are numbers arranged in a specific order, which we will vectorize, of course. But in any case, the points are such that when you pass in this grid representation, when you pass from one point to another, you see these are 2 contiguous points. The difference in the value of the property, the potential in this case, is small. This means actually you don't have a lot of correlation in your system. It means that you don't have a random matrix, a random tensor. You've got something in which the properties vary smoothly. And this is a nice property because this is the fact that enables the possibility of this compact representation. And something very relevant, which is not always taken into account, because in the end, what you will see, we will talk with something that is and resembles a fitting method. And something which is very relevant is that even though in the literature, people typically talk about fitting methods as such in the quantum molecular science community, one has to be very careful whether you've got a bound or unbound system. So the bound system is much easier to fit than a bound system for obvious reasons. So as I said, we start with something which I call an unstructured tensor, which is a bunch of numbers, which in principle do not have an obvious relationship to one another. Indeed, each of these numbers, they are just the result of one of the quantum chemical calculations, with the method of your choice. Or, of course, these in the end will come in the form of a routine that we will fit and so on. So what we want to do, we want to re-express, I call this refit. So this unstructured tensor, we're going to rewrite it in this form, and we're going to do some operations. The traditional one, it's the Tucker method, will lead to something like this. This tensor will be expressed in another tensor of the same number of dimensions, which we call core tensor, but it's smaller. So you are saving data. And then you've got some what we call factor matrices, which actually are the discrete form of the basis sets, if you want. So we can see something like that. More algebraic representation, something like this. Okay, so what we do is that every single grid point here and the associated value will be approximated by this expression here, this Tucker expression. So the message to take home is that it's better, instead of storing the whole thing, just to store these parameters, and each time you can compute this. That would be the message. So just to give you an example, I'll show you a picture. There's a picture somewhere here. Now you've got this picture is a matrix, a black and white picture of this number of pixels, this number of pixels. So in a sense, you can imagine already in terms of basis sets, I've got 2 degrees of freedom, and the maximum rank I can get is actually this number and this number, and these are the ranks. Okay, so if I've got 0, 0, I've got this. If I've got 1 basis set, I've got this. 2 basis sets, I start to see something, but still you can see already the information contained in each degree of freedom somehow. Okay, and then you've got the coupling between degrees of freedom. We start making this feature 10, 20, 50. Okay, 50 is already something good. So remember the full rank was this thing. Okay, so it means that actually we can throw away a lot of information. That's why I alluded to this dimensionality reduction. So the question I asked the community, so this is more an internal joke, who's this guy? And this guy turned out to be Tucker. Okay, so yeah. Anyway, so he actually worked in the psychometric community, so he's not known to us, so to speak. Anyway, so how to do this Tucker decomposition? There's two methods. So just for historical reasons, let me tell you that the pioneer was this method by Andreas Jäckel and Hans-Dieter Meyer from Heidelberg. But then in the mathematical community, it was rediscovered. They do something different, but actually they resemble a lot. They are a bit different, okay? So this is called like high order singular value decomposition. And actually in the mathematical community, in the machine learning community, they know this algorithm, but they don't refer to this one, which was a few years before. But anyway, so they are really equivalent in a sense. It's not proven mathematically, but they lead to the same result, so to speak. So we are interested in what we call the sum of products. These obvious reasons. You've got separable terms for dimensions. Multi-dimensional integrals can be separated easily in one-dimensional integrals, so low-dimensional integrals. So how to do this is the following. Initially start here. You compute your potential in full, which means you need to all the information in the full grid. This obviously is not practical, but let's see how simple it is. So this can be represented like that, and then you do simply a reshape, and you end up having a matrix like this. Then once you've got this matrix, you multiply these two matrices, transpose one another, and then you end up having this. These matrices. You see, you are going to contract through this index here, and you end up having a matrix which we call a potential density matrix. It doesn't really matter the name, but you can see I've got my property expressing full. I reshape into a matrix. I compute a density matrix, and I end up having this. And then how do I get my expression? I take these matrices, one for each degree of freedom. You see this kappa represents a specific degree of freedom. In the case of 2, I do this twice, 3 times, and so on and so forth. I diagonalize that. And then my basis sets, what we call the core factor, the factor matrices, I obtain them directly from the eigenvectors of this matrix. These coefficients, I'm not going to get into the details, but basically you obtain them by multiplication of these basis sets through the exact potential, so the exact potential. And then the eigenvalues will give us an idea of how many of those terms I need. How is that? I look at the eigenvalues, basically. This can be automatized easily. And then you say, okay, because actually this relates to the actual value of the potential. So I can easily estimate how many functions I need to get the accuracy I desire. So this method, as you can imagine, I alluded to several operations. So first of all, you can see that I need to compute the whole grid, and this is not practical. And beyond, actually, this goes beyond 10 to the power of 9 grid points, then it's over. You could do that, but it's not practical in any case. And this relates back to the integer overflow back then in the old times. So how to do that? There's several methods, and then as I was working with Hans-Dieter Meyer, we came up with the first variational method because we're interested in variational properties in order to make sure that when we put something more in our method, we systematically convert to the right answer. So the first one was this one, multi-grid pot fit, and then what we did, we obtained the same expression as before in this pot fit, which I described before, but we did that with a series of grids. So we avoided the full grid, and then we took several smaller grids, and we obtained partial information from those. Then we combined it together to get the big picture. So we did not lose number of dimensions. We kept the same primitive grid, but we could compute the quantities for the primitive grid, fine grid, through a different way, avoiding the full picture. So this method worked well, and I'll show you some results. And then after that, a series of very interesting methods came up. So there's one I'm going to talk, and maybe I'll mention later, which is a multi-layered pot fit, which relies in a different architecture, a different structure. And then you saw this Monte Carlo pot fit, in which the idea, which was great and was later exploited in another method, was to compute through Monte Carlo methods these quantities density matrices that we use to obtain the basis set. So it was a great idea, and it worked pretty well. So of course, any of those methods can profit from this idea of computing the density matrix like that. So that was a picture back to 2017. And then we were happy to compute the eigenstates and infrared spectrum, which I show here, of this molecule here. Okay, these are two hydroxide molecules sharing a proton. The proton is delocalized. It's a 9D proton, it's nice proton. You've got large amplitude motion. You've got everything, all the features that make a problem interesting. And then there was Mark Johnson. He was just computing the action spectroscopy, because these are charged species. You cannot isolate that. So in order to be able to compute something that resembles the infrared spectrum, you will need to use some host, some guess. And the guess he used was argon atoms. So it's always the question, like in called matrices. So does the matrix, does the host, does this friend here perturb your signal? So in principle, you assume you've got a very good signal. So the black signals here is experimental data. So these should correspond to the infrared spectrum of the species we are interested in. So what we did was to compute. First, we computed our potential energy surface with the method I showed you before. The first thing to notice is that the original surface would require, if it had been expressed on the grid, it would require 134 gigabytes. But after our reduction, we got a representation of 1.7 megabytes. So from something that would require, yeah, not massive power, but something which is already heavy because you have to store that memory. And then with this can be done in a laptop. Actually, we did this in a supercomputer. That's the truth. But in principle, you can do this calculation. You can run this calculation. It was back in 2017. Anyway, so what we observe, that a very good agreement. Of course, this is normalized. There's no scaling whatsoever. There's only normalization. So the relative position of the bands is exactly what we computed. So we did a long propagation. And then we computed this. So we were very happy to have, we already knew we had the position of this band was exact. And then the rest of the spectrum was a fantastic agreement. And I always say the same stories, like a joke, but it's true. In this case, it's actually theory that is going to guide experiment, because actually the discrepancies you see that we don't hide, actually they show the effect of these species on the spectrum. So we are really happy it was working, but still, if you want to go beyond, this method is also limited. This method actually, Muntean-Porfir, goes up to, say, 12 dimensions. But before that, let me come back a bit to the big picture. So essentially, when you do quantum dynamics, there was a decoupling between the community of quantum dynamicists, people who have the know-how of how to do wave packet propagation, and the people computing the potential. That's what I represent here. That's this is Hans-Dieter Meyer from Heidelberg, and then he understands quantum chemistry, but he has quantum chemistry calculations. And you've got here Joel Bowman and Bastian Brahms. They came up with this great method back then with the permutational invariant monomial. So it was a fantastic method to fit high dimensional polynomials. Then you say, listen, I'm interested in this system. Would you compute that? Or may I use your surface that's already decomputed? This is the way it works. And this decoupled scheme is not practical. It's not practical because you want to do quantum dynamics, but at the same time, you don't want to be dependent on someone else. And that's why when I was working with him, so I wanted to achieve what we could call a gray box method. Something was almost automatically to give you the potential in the surface in the right form. This is what I'm going to address. Now I'm going to talk about this possibility based on all the previous. So of course, one has to acknowledge the fact that to avoid this scheme, you've got direct dynamics approaches in the field of quantum dynamics. Okay, so you've got like Graham Wirtz ideas, Irene Bohatz. You've got also the GMCTDH partially. Then you've got everything related to neural networks, and then I was working on these terms, and I thought it could be a good idea. This thing. Why not fit in directly a tensor? Use the tensor structure like a parametric function, and I will discuss why this could work. Oops. So prior to that, actually, we tried something brute force. Why not try brute force if it might work? Then you've got also Ivanos Celedets, who's got his tensor train thingy, like DMRG kind of stuff. And then what he did, he said, look, to compute my tensor, I can compute in many small grids, and I can compute directly quantum chemistry. He did that, but it was far too expensive. And then the solution that we came up here was just to say, listen, can we improve quantum chemistry to make it as fast so that for every grid point, you can compute quantum chemistry? And then the idea was just to reparameterize an empirical to make it as accurate as possible compared to, say, some couple cluster thing. And then we did that, and then we obtained results which are acceptable. So these results that you can get through these, they are good for chemical problems, but not for spectroscopy, variational spectroscopy, which is our main interest. So let's discuss about this form. We're going to dissect this form to see why this could be a good idea. So we will need, remember, to get this, we will need to get those guys, and those guys. Yeah. So the first thing I'm going to show you here. So please, all these figures, the only thing you have to imagine are the dots. I put only the lines just to illustrate the shape, but you only have the dots. What are those guys? These guys are the factor matrices. So for each degree of freedom, you've got a matrix, a factor matrix, and each column is like a basis set, discrete basis set on the grid. So essentially here, where you've got the value of this discrete function, I insist that we only have the points, discrete function, and this is a degree of freedom. In this case, this is OH stretching. The choice of the points is automatically through the DBR scheme. So what you can see is that for low values of J, means the first basis set, second basis set, and so forth, so on and so forth, you've got a well-defined shape that can be easily fitted. This suggests the idea that we could put an underlying basis set and fit that. However, if you go up, then you start getting something noisy, as was noticed by Tucker Carrington and Sergei Mansov. And actually, I noticed this as well. So there's some sort of numeric instability due to associated some diagonalization. Doesn't really matter, because what we observe is that actually, even for these 9D problems and beyond, you can live with low rank approximation. So in that sense, we need this information. That's a message to take home. So we've got the possibility of fitting functions with some basis sets, and then having a small number of basis sets. And then we have solved this part of the problem. Now we have to look there. So this is the number of basis sets we will need. This the shape of the functions, we know it. And this thing here are the coefficients. These are weights of those. These are, you can see these as Hartree products if you want. These are the weights associated to those configurations. So the question is, look, you've got many indices here, though you've got plenty of those values. So how many of those you need? So to illustrate you the picture we've got here, I did a simple computation. Okay, doesn't really matter the system, it's a 6D system, HONO. And then I computed such that you've got 20,000, around 20,000 of those parameters, 20,000 configurations. So the question would be, how many of those configurations you need to get something accurate? So I show you two different levels of accuracy, what I call vibrational spectroscopy accuracy, around 1 inverse centimeter, and what I call chemical accuracy, around 350 inverse centimeters. So out of these 20,000, you see this logarithmic scale. You start making zeros. So you set up a threshold, say, okay, if the value is lower than that, 0, 0, 0. So you see that to get vibrational spectroscopy, you need only a few thousand terms. So out of the 20,000, a few thousand terms is a very good ratio. And then if you want chemical accuracy, you need just a few tens, 100, something like that. Okay, so these are the good news. We don't need many of those configurations, and we can fit those. So essentially what we did from this form, this is a function on grid space, discrete, so there's no actual function. Then what we do, we take these factors, and then we turn them into some expansion, some basis function, whatever. We use for simplicity Chebyshev functions, but you can use depending on the potential, okay? And then you can prune these coefficients, and then you end up with an expression which is an analytical expression. So essentially what we did, we turn a grid representation into analytical form. And we call this finite basis representation for obvious reasons. And then just as a remark, I was surprised because I thought it works well, as I will illustrate later. And I was surprised not to have seen any mathematicians or anything do something similar. And then recently, only recently, like a few years after the publication, like it was this year actually, just looking, I found this obscure journal from mathematics, and it seems that people did this for 3D with singular value decomposition. So I was happy to see the mathematicians also were there. Okie dokie. So this is a big picture. I told you I want something gray box. So it's not black box, but it's almost black box in a sense. So essentially, we just do a combination of global and local algorithms. Why? Because we've got many, you've got a parameter space which is relatively large. It's not small. Good news is that we found that actually you can freeze those two guys. What are those guys? I can freeze the number of configurations, and then I will only optimize the number of basis set functions and these coefficients. And then essentially we just create swarms. We use these libraries which are highly optimized in every language you can imagine. And then you create swarms of walkers, and then they will find hopefully a good minimum, potentially the global minimum. Okay, okay. Oops. So just to show you whether this works fine or not, we did a test with the traditional method, reference method, pod fit. Remember the other methods after pod fit, the other flavors, they are just approximations to pod fit. So they are never as good as pod fit. So pod fit will be the reference. And then I've got here a number of basis functions. This C will have different meanings. In our case, we've got a C which is smaller. This is a bit bigger. In any case, we see we get consistently a factor around 7. Here, not, but it doesn't really matter because you're very good accuracy. So these were good news. This potential, it's HONO, is a 6D potential, and this is fully automated. We didn't do anything apart from saying, okay, I want these many basis functions. That's all. And then consider a bit more like potential in the surface properties. Just have a look here. So we did not include any specific information of the topography, no stationary points included. We just gave for computational reasons, we gave a coarse grid, a small grid as a reference. Could be a list of points, but we gave a grid as a reference. And then, as you can see, every single, we've got a trans minimum for HONO, we've got the cis minimum for HONO, and the transition state between these two guys. And in this 6D surface, you observe that without explicit inclusion of those guys, we get exactly the same values, okay, down to 10 to the minus 3, whatever the units are, atomic units or radians. This inherits some properties of tensor decompositions. So the first thing is that these optimized factors, they are almost orthonormal. This actually is a good thing to have. You're happy when your functions are orthonormal. Then, of course, you can symmetrize by ansatz. So this we are doing for electronic problems. You've got two electrons which are should be equivalent. You can symmetrize. You can enforce this symmetrization, which is very nice properties. And then, of course, you can have this what we call effective sparsity. The core tensor is not sparse, but you can treat it like as if it were, because you can remove so many and leave it essentially with a few zeros. But nevertheless, in this you have noticed for sure, the core tensor grows exponentially. So we are limited still. We have the same limitations at default. And that's why we look for new solutions. And the new solutions are those in terms of what we call canonic polyadic decomposition, which I represent schematically here. You start with your unstructured tensor, and you do some operations, and that's a key point, some operations we call CP, and then you end up having this form here. Now you see what used to be a tensor, now you've got a collection of points, so it's essentially a vector. These weights constitute a vector. How many of those you've got? You've got R, which we call the rank. And then the factor matrices, they look like small vectors, if you want. So this form is much more compact than Tucker, but much more compact. So for a few rank, you get amazing accuracy. Two methods. We're using this one from TensorLi libraries, typical alternative least-square method. And then there's a fantastic development by Marco Schroeder from Heidelberg, in which what he does, he applied his Monte Carlo knowledge to the alternative least squares, And actually, he came up with the alternative Monte Carlo version of the alternative least squares method. So let's compare these two guys. So we said that here you've got a tensor, so you need many parameters, and here you've got a vector. You actually need way less parameters than in this case, but there's no free lunch. These guys, these functions are very nicely behaved. They are orthonormal, almost, but these guys are just horrible. They can present very nasty behavior, okay? And then actually, it's actually the actual process of achieving this form, this CPD thing, which is a mess, because the algorithm gets lost. You don't have a well-defined path to find that. Okay, so most of the time you end up having this sort of numerical issues, like in you can have these numerical issues that lead to linear dependency. It's actually the basis set. They are linear dependency. It's a chaos. So even though this has a lot of advantages, and then we are going to deal with that now, because we wonder, can we turn this into analytical? So it was as straightforward as before, but we managed to do that. Let me just, yes. So let me tell you why one would like to have these expressions, okay? So let me show you a problem, a real problem we're dealing with. Well, actually, it's Natasha who's there, who's fighting against that with the help of Lei, who's also there. So we've got this problem here, which is methane on top of a surface. A lot of coordinates, 15D problem. And then the idea was the following. We need this product form to do dynamics. That's a priori condition, fine. But then the question we asked is, in principle, you don't know how big your primitive grid should be. You have a rough idea, but you don't know exactly. So it means you have to make some tests. So if, and this if is actually provided that, so if your refit method takes long, takes 1 week, takes 2 weeks, take a few days, every time you do a new fit and then you compute something to realize that your wave function is not converged, you need to start over. So that's why we thought that maybe the idea of having this analytical form would be also a good idea. Another case, just now you converge your wave function, you're happy with it, and then now you suddenly decide the experimentalists have such energy of the initial wave packet of this thing, then you have to change again your grid. Or you realize that you don't have enough number of points on this dimension because now you decided that you want to study a bit more some torsion or whatever. So this leads to the idea that why not trying to turn this into analytical and then only interpolate, get once from a coarse grid and then interpolate. And this is what we tried to do. And it turned out to be a bit more complicated than we initially expected. And this is basically the scheme. Let me start by saying that after thinking and much discussion, we realized that we needed to know what we were doing. And then what we were doing is that we had an hypothesis, which is this one. That exists such an expression. You see, you've got a Canonic form, which is this form here, in which you can express this. Okay, there's nothing new because it's everything I've been telling you so far. And then how to do that turned out to be a bit of a complicated thing. So first, we will work with some reference, which I call coarse grid. And this reference must capture all the relevant information contained here in terms of correlation between the degrees of freedom. This fine grid, primitive grid, is the grid on which my wave packet will propagate. So it has to be dense enough to be able to provide you converged dynamics. So we've got our CP, we've got a seed. We do a CP decomposition. That's why I show you two methods. So we've got a CP decomposition, an initial one on a coarse grid. So one has to look for a favorable scaling between these two. So these will be much cheaper than that thing. That's the key point of that. So we do initial decomposition, and then we do as before. We keep the coefficients. Actually, this is reminiscent of something, these methods I alluded before. We knew that the coefficients in a coarse grid, they already capture most of the correlation. So they already indicate which type of configurations you have to put into your formula to get the whole correlation. So that's why we could say, okay, this is fine. So these weights associated to some configurations, or the other way around, the configurations associated to these weights from the coarse grid, they are the good ones, even in the fine grid. That's the thing. It turns out to be true. Then we do the interpolation of the factors. Of course, this implies that your factors, they're smooth. And then to do this interpolation, we've got this intermediate representation in which we fit this, okay? So in a sense, actually, so first, we are turning an algebraic representation into algebraic problem into an optimization problem. And second, here, you might not see, but actually we do some sort of a mixture between continuous and discrete optimization. I'll describe that later in this next slide. Okay. So let me show you a small example. Needless to say that I'm going to show you an example up to 9D. And now we're working on 15D. So these examples, they all work perfectly. So I'm not going to bother you with some data. I'll show you some data later, some vibrational eigenstates. But now we've got this 6D. If you do Tucker, you will get something of the order, the rank will be something of the order of 1,000. With these, you get rank 200, you get something very nice already. Okay, so this is a Tucker form. This turned out to be the maximal rank of this potential, okay? And then we, by doing our optimization with a complete different method, we ended up having something that really resembled that. So we were happy that it was the amount of basis sets we needed in this method and that method was similar. And that was good news, because actually you can show mathematically, you can transform one expression into the other. Okay, so this was, we were happy about that. Then what you see here, what we do, typically you need some reference data and some validation data. So you're comparing at all times, because actually this can overfit. Okay, so you're tweaking your parameters, and then you increase the number. You do two things. You increase the number of, expansion functions, and then you optimize those guys. Okay, so essentially what you observe that in this case, which is a finite range case, that's a particular one. I'll show you a general case in the next slide. So in this case, you see that both the fine grid and coarse grid, the error goes down. Okay, so but in general, you will find this picture, which resembles what you know from machine learning cases, in which when you compare those two, actually, you can saturate the information of the coarse grid by adding more and more Bayesian functions. You can be exact on the coarse grid, of course. For a limited amount of information, you put more functions, you end up being exact. But the validation, which is a different grid, and is not even the coarse grid is not even a subset of the fine grid, not necessarily. Then we will be good, and then at a certain point we start having some discrepancies. So we've got this overfitting. So the algorithm is such that this is a 9D problem, methane, this is an interesting molecule, rank 250. This means in MCTDH language, it means you've got 250 lines in your operator file. So the algorithm will stop there and say, okay, this is my optimal solution, and then we end up having our expression. I told you I will show you some more precise data. So now we compare here NCCPD and CPFVR. And actually one has to, we do a sampling, Boltzmann sampling, so that we fix some temperature. We want to focus on specific region of the potential to improve that description of that region. So this is the target region. So this part is not important, but nevertheless well treated. But this is the region. And as you can see here, CPFVR and CCPD, they give the same result. And what's the difference between these two? The difference, I think it's somewhere here. Yes. So, no, I didn't put it. Sorry, it doesn't matter. So let me come back up to do MCCPD. We do MCCPD on the fine grid. But to do CPFVR, we do it in a coarser grid. So we gain a lot. This can be an important factor. I think I've got some numbers here. Yes. Okay, if you do, for instance, in this case, this is 9D. If you do full grid CPD, the composition CP takes 26 minutes, and this takes 8 minutes. This is not great. This is not a match. This is a 9, but it's expected to scale, obviously, with dimensionality of the system. So just to show you some numbers, these are vibrational eigenstates of methane, full dimensionality, experimental value, reference, some diagonalization from some people, yeah, Zhang and Fabian as well, yeah. And MCCPD and CPFVR, you can see the numbers are Very good. So we're happy. This works. Okay. So what did we show you here is that we are able to get high dimension and analytical operators that can be extrapolated. Okay. So something, this small sentence, actually, it's a key point. The Boltzmann sampling is useful for bound systems. And then what we are doing now, we are just exploring all the types of sampling in order to get something which is adequate for molecule surface scattering problems. The big picture is the following. All this is is going to be included in a a package which relies on other libraries. And then the idea is that you've got some parameters from a given model. You decide what model you want. I showed you Tucker and Candecomp or Parafac or Canonic polyadic decomposition, but it can be other models I will show you later. Then you compute the current level of accuracy you've got for whatever property it is. If it's good, you've got the optimal parameter. If not, you tweak the parameters and then you start over. You've got, of course, you compare with your reference data. So this works for these tensor decomposition methods. And now we are advancing, going forward to other tensor decomposition methods. Just let me, I didn't talk about this, but we've got ways of automatically generating what it could be argued the optimal set of points, because we've got some methods that are able to map full potential in a surface, and these two sets of boundaries, of course, and find all transition states. Those transition states, we are able to find out all minima, so that from those we can scatter points and we can map perfectly and recover the whole topography of the potential in the surface. So there's a software automaking which does that, even for non-covalent systems. Actually, this was our contribution. So summary and conclusions. Well, I hope I showed you and you understood that we've got this, what we call finite basis representation, which is a way of turning a tensor decomposition expression into analytical form. We applied it so far to Tucker and Candecomp. And what are we doing now? We are doing a few things. This is going to be applied to electron dynamics. Why? Because electron dynamics requires a huge potential, as I showed you before. We would like to include this in a diabatization scheme. It must work, like a vibronic coupling model, like those of Graham Worth. This can work. You've got analytic expressions for the gradient and the potential itself. We're working on the multi-layer extension of that, which is very powerful because you've got a recursive scheme of computing potentials. This in collaboration with Frank Otto, who's in London. We're thinking of using this in direct dynamics, in any flavor of direct dynamics. It could be used to propagate Gaussian wave packets, or to any direct dynamic, where you to instead of a trust radius region, you end up having this type of expressions. And this hopefully will be soon interfaced with MCTDH and Quantix. This is just the form we would like to get the potential. Will be exactly this. It's called multi-layer form with Frank Otto. And then finally, just thank the two main actors in this thing. Of course, they here, Ching Fei here, Hans Dieter Maya. So we've got Ramon, who did the initial work on the initial methods. Natasha, who took the lead now for the CP, which is a very complicated problem. Let's thank as well friends and collaborators. Marcos Witters as well, Take Character, Frank Otto, Marcus Ora, Dieter, Guido van Rossum. We never thank these guys, and they make our life easy. So Guido van Rossum, thank you. Travis Oliphant as well, Janko Salfi from TensorLi, and you for your attention.
Thank you, Danny. Questions? Oh, sorry.
So in the last part, in the last part, you mentioned that you use Chebyshev polynomials.
Yes.
And I wonder if you compared with Morse polynomials, if you could use Morse polynomials.
Yes. In principle, so let me show you. So the answer is yes. You can use any basis set, and actually, this it was written there. I didn't mention it. So the basis set the choice of the basis set in principle could be automatized, but typically we observe it with your eyes. And these topologically similar potentials, they share the same basis sets. This is something that I haven't really stressed, the fact it was in one slide. So what do I mean by that? If you've got a system, molecular system, you are going to have some stretchings, some angles, you're going to have some torsion possibly. So all these potentials, actually, but in a more loose sense of the meaning, you will have more potential for all the stretchings. And the answer is yes. What we did, if you let me come back to here. Yes. Why did we use Chebyshev? Because it's a general. They've got some nice properties, hidden properties, but they ups here. So this was a topological thing. So could this be fitted by a Morse? Yes, yes, yes. A bit less. So that's why we use this general, unspecific potential. But for other problems, you end up having trigonometric function and so on and so forth. So this is something ongoing research too, because the idea in the end is to put some basis sets so that you're going to compute your potential, and then you do the potential by putting some basis sets specific to your system, some particles or some molecules. So I've got a molecule, I take my basic Chebyshev function or whatever, they can be even pre-optimized, like Gaussian basis sets in electronic structure. It's the same idea.
No, that was just because usually you save, yeah, you could gain a factor, I think, with.
But then the difference is the following. So I rather use this instead of that, because then what we are doing nothing new. We're doing just a fitting as we used to do it, right? You've got a torsion, you put a cosinus and so on. But here's different, because actually I could argue, we can discuss about that. These are the natural representations of a potential. Why? And I say natural in purpose, because actually they are the natural potentials. They come from the diagonalization of a potential density matrix. So the orbitals of a potential are these guys here. In Tucker form, they resemble like that. They bear some resemblance with a potential, with the specific stretching or whatever. But if you look at it is also true with CP, okay? So in CP is more what you mean, because CP can be related to component analysis if you want. So oops, so here. So this is just to show that CP can be very nasty, but if you've got the right rank, then you end up having something. Look, you see a mess here, but you have to bear in mind that after diagonalization, you've got a random phase. So that's why you got some guys up and down. But if you have a bit of imagination, you see you've got always the form you alluded to. Yes, you've got something like that. So the CP, which is a proper component analysis, in a sense, CP will reflect what are the types of potential I put to compute my full picture. Knowing that you've got some weird behavior, like, I don't know, here, okay, this is a perfect Morse potential. It goes a bit down, but this reflects the fact that they are nonlinear independent. So you're mixing information from other degrees of freedom, and so on and so forth. So the answer is yes, but I'd rather not do that, because then I lose these properties I mentioned. I want to have my orthonormality, and I want them to be related to the initial Schmidt decomposition for 2D.
And I have another question about, so you say that you are going to study now electrons?
We did already some work on electrons, yes.
And course, potential shape are quite smooth.
Yes.
And with electron, they may be not.
Yes, it's true. That's why I put it on purpose. This is something. It's been a while I'm writing the paper, so that's why on purpose I wrote this sentence here. I insist on this topologically. So you've got a singularity, and this makes not topologically equivalent to a molecular potential, and that's why the functions, they are different. They do not like that. They do not look like this. That's all.
Thank you.
Thank you.
Online or no? On site.
Thank you, Daniel, for this presentation. Question on this slide. You said that the factor become noisy. is it really the oscillations in the bottom part have a physical meaning here?
Yeah, probably you're right. So when I say noisy, it's a noisy for us because we cannot fit them. It wouldn't be because they are. So if we fit this thing here, we will need a very high order. Then we lose the whole picture. For the type of problem you're interested in, they are a bit more accurate than ours, I think. So we will need more of those functions. And then that's why I only refer to two things. I'm not talking about rotational spectroscopy. I'm talking about, even though we might get there, but vibrational and chemical accuracy. So you're perfectly right. There's some physics inside them. Yeah, there's some physics which we neglect because we can afford to neglect it. So this will lead to the fine subtleties that we make a barrier being, say, 1 inverse centimeter above or below, something like this. Could be something like that. So these functions, they are responsible for the big rough pictures of the potential, the hard exponential wall, the deep chemisoption well, whatever. So these are responsible for that. The mixture of them all, of course, in all degrees of freedom and so on, and the interaction. And these that we neglect will make us lose curvature in some regions, so on and so forth, which might lead to some state being a bit less, have a bit less spacing that they should, or something like this. But it's good enough for our purposes, as we've shown, even for vibrational spectroscopy. They compare very well.
Okay, thank you.
Okay. I don't see questions online. So I have a question. So if I use machine learning lingo, can we see all your method as some forms of kernel regression?
Yeah, I don't see why not. Yes, it's sort of, because actually you end up having the same functional form. You've got a product form there as well.
Yeah, right.
And actually, well, let me come back to the. I mean, oops. Student visiting, and he works with
this kernel
regression, yes. And
yeah, because I mean, all those
we're exploring the link between this picture and the other. Actually, he's got this expertise and from the group of Qing Men, and then yes, this definitely yes.
Okay.
There's a clear link.
Yeah. I mean,
Because
it's
the
at the end,
yes.
it's the same, right?
Yes.
You just pick a kernel, so that would be your your basis function that you use.
Exactly.
And, yeah.
Oops, sorry.
But then in regression, they use some form of regularization to avoid overfitting. So could you do that? Because you see that if you increase your orders, then you have this overfitting. But maybe you can have some kind of regularization, L1,
So
L2,
that's
whatever.
a good point. That's a good point. So there were two ways of doing things. So now let me talk about as a PhD supervisor.
Mm-hmm.
So there were two ways of doing things. So you could, so this is what you want to see. Okay, so you could do the following. The way MCCPD works is the proper way, which means that you've got time to set up some equations of motion. They're not equations of motion, they are just equations to optimize. So you end up having some equations that guarantee some properties, as you were mentioning, that you guarantee, you impose ortho in the whole process that your basis functions, they remain orthonormal or remain normal, whatever. Yes. Okay. So basically, I know, but we didn't do that.
I see that would be your regularization.
We've got some equations written, but we didn't implement the equation. So yes, it will be, but it works so far. So for the sake of advanced PhD, we decided to take, not to take the risk of.
So that would be some kind of physically regular, physical regularization or something like that.
It's actually pretty straightforward in the sense that you already have some beautiful equations from MCCPD, and then you can just make a one-to-one map into these equations, or you take the ALS equations and you only have to apply an extra constraint, including these new expressions of the basic underlying basis.
Okay, cool. Thanks.
Thank you.
No questions? Then thanks again, Danny. And yeah, a morning session.